Yeah.
The red light's on, so we must have started.
Cool. So we are on, and we're in Singularity world again with the usual suspects who we'll introduce again, and a new face. So let's go around. Let's introduce ourselves.
I'm Jim Larus. I'm a researcher in Microsoft Research. I do programming languages, programming tools, parallel computation. That'll look unscripted.
Yeah. So, parallel compilation. Cool.
No, parallel computation.
Certainly.
My name's Mark Aiken. I'm an engineer attached to the Singularity project. I used to work on the engineering side in Windows. I was in home networking, and I got to be part of the Windows XP launch, which was really exciting. And so this is a bit of a change for me to be in a research environment. And lately I've been working on hardware protection features, and working on resiliency, and a host of other things on the Singularity project.
Excellent.
And I'm Galen Hunt. I run the operating systems group
Excellent.
inside the Singularity project.
Perfect.
So Mark works for me.
All right.
Or I pretend he works
See,
for
a good
me or
boss?
something.
Nice guy. He's like a nice guy.
Largely because he lets me pretend sometimes.
Review time. The answer to that is honestly yes.
Of course, the answer is obviously.
Very cool. So what do you want to talk about today? You want to give an intro? I mean, this is the third installment of Singularity on Channel 9, so the viewers are somewhat up to speed on what's going on. But for the new ones, let's talk about what is Singularity?
So Singularity is a project we started in research almost 3 years ago now to rethink how software is constructed, with the idea that if we thought about the issues afresh, we would be able to build a system that was more reliable than what we have today. And so we basically said we'll start from the bare metal and rethink a lot of the assumptions that people use to build software and see if we can't come up with something that's just built better from the first place. Okay. So, the three things that we've focused on so far are: one, safe programming languages. And Singularity, for the most part, with a little bit of exception, is written in C# or an extended version of C#, and we use the safe dialect of C#. So we don't worry about things like buffer overruns, because in C# they're detected and they get turned into exceptions, and so we don't have unobserved buffer overruns that can be exploits. Another thing we've done is we've changed the architecture of the system to allow us to have a lot more resiliency in it. I mean, our goal is basically not to write software that will never fail, but write software where pieces of it can fail either because of software errors or even hardware errors, but the system as a whole keeps going. And then the third part is verification. We would like to increase our ability to mechanically verify the properties of the system that we care about, so that we can find the errors using tools more easily, so we don't have to find them by debugging or after we ship them to customers.
Excellent. So I guess one question that comes up, I interviewed, I guess he's the leader of this division now, in the sense that Craig Mundy, and he was talking about the composability of software and how, in his opinion, software engineering really isn't engineering in a strict sense of the word, because it's not composable in that sense. So what you're talking about is developing a platform and associated tools that'll make it easier for software developers to build components that they can then reliably think aren't going to completely mess up the rest of the system. Is that what you're
that's in part it. I mean, software engineering isn't engineering, and computer science isn't science. so in Singularity, we have definitely thought about this composability issue. One of the ways we're doing it is the Singularity uses what we call SIPs. If you go back and watch the earlier videos. SIP stands for Software Isolated Process, and a SIP is a closed unit. It's what we call sealed. So the code that's in there is all in there when the SIP starts executing. There's no dynamic code loading. There's no runtime code generation, so that we know what's in there and we can do a better job of doing optimization in the compiler or verification in the tool. But more than that, SIPs don't have shared memory with other processes on the system. All the communication between a SIP and the outside world or another part of the system occurs on channels. And if you remember back to the discussion in the previous movie, we explained how channels come along with contracts, and we actually verify that the code in the SIPs obey the contract. The code on both sides of the channel obey the contract. And we can check this statically in the compiler. We can find a lot of errors in the code that way. And this goes right to Craig's comment, which is we are increasing the composability of the system that way. So that, if you have a process that communicates over channels, you can combine that with another process that communicates over channels much more easily than if the process is at shared memory. You have to worry about getting the locking convention for the shared memory correct, because locks are not composable. I mean, you have to know what the locking convention is with a piece of code to be able to interact with that piece of code. A channel, on the other hand, all you have to know is what the contract is for the channel, and that's something that doesn't require you to know what the implementation of that is inside a process. And so you just look at what the channel is supposed to do and you say, okay, if I can follow that, then I can interact with there, and I don't care how it's implemented within a process. And that's the real definition of composability. It's not that you don't know anything about it, but that you only know what it is at the higher level of abstraction. You don't have to delve into the implementation details.
So it's layering.
It's definitely layering.
Another way to say it is it's predictable. It's much when you bring two of these components and put them together, you can actually predict that what's going to come together is going to work correctly. Okay, because you can verify either side and say, yes, these conform to this contract. So when I put them together, they're still going to work as a collective.
Right.
Whereas if you had shared memory and locking,
Sure.
you might be able to plug them together and it might even run today, but you don't know that it's going to work tomorrow.
Exactly.
And that's actually one of the really cool results that Microsoft research has come up with in the past couple of years, is that it's a theory called conformance checking, which involved a couple of researchers here, and Tony Hoare in Cambridge, and Robin Milner, actually, who's a very famous computer scientist as well. And what we showed is that if you have these channels with contracts, and you check each process's use of its contracts locally, you don't care about what the rest of the system is, but you only care about whether a process obeys its contract, then you can show that the system as a whole, all the processes and all the channels and all the contracts, are deadlock free. So it's really a fantastic result. It says that you just check things locally and make sure you obey these local contracts, and you get this very powerful global property that the system as a whole is deadlock free. Which goes back to what Galen said, is that you can get system properties just by doing local reasoning, which is incredibly powerful, because if you have to understand the whole system, it becomes very difficult for programmers to get it right, and very difficult for software to evolve. And it's also very difficult for tools, because the scale gets to be so large that the tools start to break down.
Absolutely.
As a sort of meta comment here, I imagine that a lot of the audience is actually people with a stronger engineering background, since there are many more engineers in the world than maybe there are researchers. Come on. Microsoft in particular employs many more engineers. So one of the things that I've found really interesting that I'm sort of being reminded of as Jim and Galen described this, is the extent to which it's interesting to be on a project like Singularity and research projects in general, because you get to re-examine a lot of these basic assumptions. A lot of the sort of stunts that we can achieve that are interesting, like composing a software system out of a bunch of pieces, and you verify them locally, and then you can say, aha, you know what? I know now, having examined all the pieces individually, that the entire system will run deadlock free. There's these interesting results. People are like, wow, that's great. You haven't even run it yet, and you know that there won't be any deadlocks. How did you possibly do that? The way that you can get to that kind of result is by sort of going back and re-examining some of the assumptions that have been sort of baked in and lying static for a long time. Out in the real world, when we're doing real engineering, we live within a lot of constraints, right? We live within the constraints of how systems have been traditionally designed without re-examining those assumptions.
Yeah.
I'm going to have to re-examine Mark's pay skills. He doesn't real engineering anymore.
Maybe I should not say real engineering. Maybe I should say large-scale commercial grade engineering.
There you go.
I like the research quality engineering.
Well, it's definitely on a smaller scale, but that comes with its advantages as well. You can't just pick up a commercial system and say, wow, I really wish this thing didn't have any deadlocks, or I'm very annoyed by the quantity of bugs and exploits that we run into that have to do with buffer overruns. I wish I could change one of the fundamental assumptions that I just sort of unwittingly picked up when I began the project, and now write the whole thing in safe languages. Most of the time you don't have the luxury of doing that. But somebody needs to concern themselves with periodically revalidating, rechecking, and thinking, how can we best build software now, given what we've learned over the past, decade, 2 decades of computer science, and that's what projects like this answer.
Absolutely.
So we do have these really cool, interesting results that arrive largely by going back and saying, what if we didn't do that? What if we did something that we now know is a better approach than if we did things in the past?
But I mean, let's talk about this now that we're in the third version. Do you think? I mean, right now, Singularity is what? It's a research kernel, right? That's what it is.
Right.
And now it's virtually impossible to compare it to a general purpose operating system like Vista
You would think
or
so.
NT.
It's hard.
Don't you think? I mean, of course it is. I mean, do you
It's hard.
think? I mean, could it support what a general purpose operating system needs to support? You don't have any idea how people are going to set it up. You don't have any idea about the hardware. You don't have any idea about how many applications are going to be running simultaneously, what they're going to do. My question to you is it just going to always remain a kernel, or do you see it like at some point saying, hey, let's try to actually make this into a full-fledged operating system that has typical things that one expects an operating system to have?
Well,
Not a replacement
Yeah,
for
yeah.
Windows, but I mean as a research project.
I mean, in a sense, we have a full. So we'll show you later. We'll try to show a demo. You'll see what our full operating system looks like. I think one of the benefits, I'll put it this way, one of the benefits of having people on the team that have worked in Windows and have seen, and Mark's spent part of his career there. I spent 2.5 years working in the Windows Server division and really being like in the trenches, seeing the real problems. Is you can come into a research project like this and say, okay, how would we address those problems? Maybe we actually even haven't written the code. For example, plug and play. We haven't written all of the code for plug and play and being able to dynamically pull out a device and reinsert it and things, but we have a pretty good idea how it works from an engineering perspective. And so we can kind of say, okay, look, this is right here, dotted box, this is where insert engineers, okay? And so if you were going to take this and build it into a more full system, I think there's a lot of, do I believe you could? Yes. And we have some idea of where the boxes are that you'd have to in this box insert 1,000 engineers here.
Right. And tens and tens of man-years of
But they know how to do what they do.
right? And that's the proper function of a research effort, right? It's not. It wouldn't be correct for us just for the heck of it, right, to build out Singularity so that it had all of the features of a general purpose operating system, so that it booted on any hardware, so that it ran any legacy application. Then we wouldn't be conducting research. We'd be spending most of our time in sort of straight line engineering effort. So
Sure.
it's the right balance to strike, and this is a balance that we strike all the time when we do technology transfer, right? On the research side, we try to advance our understanding of the problem to the point that we think we've solved all the difficult problems, right? Whereas when you start out on an open research problem, you don't know how to successfully build the system. You say,
Mhm.
well, we wish we could do that. Is it possible? Is it feasible? Would a system that did that, ever finish running? Is it
Sure.
Can we ever possibly get there? Research is done when they've answered all of the open questions, and it's just a question of engineering effort to go and flesh out the system. And that's also the point that we try to do technology transfer at, right? We say, look, we've answered all your difficult questions. You'll agree. Hopefully we sit down and look across the table at the engineers and say, okay, we've told you all the things that were mysterious before, right? You can go build this now. And they say, yes.
And in fact, they'll
I
say,
do.
and we could build it better than you.
Yes. And
The engineers invariably can build it better
Yeah,
than
and
we
in fact,
can.
they usually
They're
do.
the scientists.
Yeah, I mean,
Yeah, they usually do.
You're an engineer, though.
They say
You
the
guys,
first
you're all
one-
engineers.
But we,
No?
the way I like to describe research is, there's this old adage that you do, I think I've actually said this on one of these, there's the old adage of the last 10% of the code takes 90% of the time.
Mm.
Well, we just don't do the last 10%. Okay? And so therefore, we're 10 times faster. Because we
Okay.
only do, the easy 90, the first 90% that proves that the concept's going to work. And then,
Fair enough, but I mean, is it fair to assume that the evolution of Singularity isn't going to be a full-blown operating system released by Microsoft in the year 2015, and rather it could be utilized as some kind of component inside of Windows, like as a virtual machine,
it
or
easily
something like
could
that?
be. It easily could be.
So-
I think what the future looks like
It was blank.
it's blank.
Good.
So, our goal for Singularity is not to write a new operating system for Microsoft. Our goal is basically to try out a whole bunch of ideas and then go around and tell people inside Microsoft, hey, this worked. We wrote an operating system, we're using C#, and look, it's pretty fast. It's faster, in fact, than the operating systems you wrote using C or C++. so that people inside Microsoft start thinking, hey, if they could do it, let's figure out how they did it and see whether we can't do it as well. And that's where a lot of the technology transfer is going to come in terms of the ideas rather than the actual code. We're not sitting here trying to write a commercial quality operating system. We're not trying to handle all of the devices that are out there or all the corner cases or all the applications people can write. We're sort of trying to get the minimum working to demonstrate the value of the ideas, because the ideas are what we're really going to transfer out of research. And this has been something that's worked pretty well already in Singularity. We've gone and talked about it all throughout Microsoft and actually through the academic community as well. And people, hear what we're saying, and regardless of whether they would have built the operating system exactly the way we built it, they hear it and they say, oh, okay, that's a pretty interesting result. I could use that part of it or this part of it in my own work, or I really think the safe languages are good, or I think the SIPs that you have in there are a good idea. And all of that is where the sort of influence of the project comes. Not so much the transfer of code, but the transfer of the ideas.
Because as Galen says, often one of the first things that the engineering side does is say, we're vaguely irritated at how you wrote this, and not invented here. And start from scratch.
But they're right.
And they're right to
just-
do that because
we didn't
they're
write the code.
better.
There's
We should maybe talk about a little more about Singularity.
Sure, but it was good. The reason that I brought that up is because that has been a question that has come up consistently on Channel 9 and Slashdot and other places. Is it going to replace Windows? Is it going to? So now that you explicitly stated an excellent answer to that, everyone.
Definitely not.
Don't hold your breath.
Great. So let's dive into the architecture of this pony.
All right. Yeah. So we wanted to come back to the. My build's working pretty good over there too, by the way. Man, are we close enough?
Oh, sorry. Hey.
All right.
Singularity.
It's a black hole.
Okay. So we wanted to come back to the whiteboard and talk about the Singularity architecture really quick and review it. And it's going to be really important for the rest of the discussion because we wanted today. There's a couple of key ideas we've had in Singularity and things that we've tried out over the last 6 months that we want to talk about.
Excellent.
And so we want to come to a review really quick of the architecture.
Okay.
So Singularity is a microkernel type system. So down at the bottom there is a kernel. It's designed to be small, minimal, and just provide a basic set of features. Okay. And then outside of the kernel, we add all of the additional features that you would think of the rest of the operating system. So for example, we have a disk drive. The disk driver for the disk drive actually sits in a software isolated process outside of the kernel. And the file system as well does. Okay. And the TCP IP stack sits outside of the kernel, again in a SIP as well. And the HTTP web server also sits outside of the kernel. Now let's say you're going to build something like a web serving application. The content generating code would also run in a separate process outside of the kernel. And so the key aspect of the architecture is that we move everything into its own individual process. And then one of the ways we get resiliency in the system is that, say if a disk driver fails, then we can shut it down, start a replacement up for it, and keep on running. Whereas in previous systems, in Windows or Linux or just about anybody else's current systems, the disk driver would have sat right here. And so when the disk, down in the kernel, and so when the disk driver went berserk, it would have, scribbled all over the kernel and messed everything up, and you get a blue screen of death. Okay.
Yep.
So we move it out. We don't get a blue screen of death anymore. Okay. In fact, we've reused blue. We'll show that when we do a demo. What a blue screen. Re-appropriated blue because we don't need it for a crashed system anymore. Yeah. And then, so inside a couple of other aspects of the system is inside, let's see, if Jim was drawing this, I'm see if I can draw a garbage can here. Okay. Yeah, so there's the garbage can. Okay, so the kernel is written, of course, in C#, and I think I've talked about this some in this. 95% of the kernel is written in C#. We have some assembly code where other operating systems have assembly code, things like that. And it has its own runtime, its own compiled runtime for its C# code. Each of the processes also have their own runtime, their own copy of the runtime, and their own garbage collector. So let's see, go back there. There we go. There's my garbage can icon. Okay, so
Okay.
each one has its own runtime. It has its own garbage collector.
Mhm.
Okay. One of the benefits of that is, let's say this content generator, real-time behavior is not really important to it. So it can have an efficient compacting garbage collector, whereas maybe the TCP stack, or say down here in the disk drive or the kernel, real-time performance would be more important. So we might use a real-time garbage collector that has a higher overhead, but it has lower pause times, guaranteed pause times.
So now, and this, your original concept wouldn't work if processes were sharing garbage collectors.
That's right. Yeah. So one of the questions people ask is, well, like, how does this compare with app domains? So these are let's see. So these are software isolated processes. We rely on type safety. Okay. And so people ask, well, how are these different from app domains or from Java isolates? And the key thing is, in those environments, there's a common runtime and there's a common garbage collector. Okay. And so if somebody real time over here might be running, and if they have to do they trigger a garbage collection, the whole system comes to a halt. Well, in this system it doesn't. Only the disk driver comes to a halt. Everything else keeps on running or whatever. Okay.
Excellent.
And again, as we've said, all of the code in here is compiled. In each of these processes, we compile all the code down through the Bartok compiler, so we're not using a jitter, for example. Okay.
Okay. And the Bartok compiler was in session 2 when David Tarditi joined us.
That's right. David was here, and we talked about the Bartok compiler. And then, of course, we have all these we have channels between that Jim's already alluded to with the contracts we communicate. And
I want to mention the kernel interface.
Oh, yeah, okay. So, and then there's an interface. I use an old term that nobody remembers, and nobody remembers what it means anymore. An ABI. Okay. There's a kernel interface between a process and the kernel. Okay. And it's not a full API like you would think it's, say, Windows. So if you go look at the Windows API, there's something like 14,000 functions in the Windows API. Okay. This kernel interface is around 140 functions. Okay. And all it is the functions that give you a pure computation environment inside this process. So it has functions to let you start and stop threads, to allocate pages of memory to this process, to synchronize objects within a process. Okay, so it's kind of purely about the computation within this process. And in fact, one of the unique characteristics of this interface, kernel interface, is that this, say, the content generation process, it can start and stop threads, but only its own threads. It cannot alter the state of any other process in the system. Okay, and the only way it can affect anything outside of itself is it can send and receive messages through channels. Okay, and so that one of the benefits of that is we can actually take let's say this content generator here, and we can take all the code that's in the content generator, and we can tell you, is this content generator ever going to try to send spam? Okay, so now how the heck would you answer a question like that? Well, the way we answer a question like that is we say, it has an interface that it plugs into the HTTP generator. But we can check, say, does it have any other interfaces to any other part of the system, any other process? And we can verify that, in fact, it does not. Okay, and so if it doesn't know how to talk to a TCP stack, it doesn't have that interface, that channel contract, then we know it can't talk to the TCP system. So therefore, we know it can't send spam, for example. And it allows us to make some, be able to look at a piece of code and make some very interesting statements predictive statements again, about what is this code going to do in the future, what it's capable of doing.
So now, what does installation look like then on this system?
Yeah, well, okay, so that's an interesting question. So installation on this system means you walk up to the system with a manifest that describes a new process, a new program that you want to introduce to the system, and it says, here's the interface on the outside of it. It also lists what are its dependencies. What are its configuration requirements for that piece of code to be able to run correctly? And then also, here's a list of the MSIL assemblies that have to be installed on the system. Okay, and then we take that manifest, we take those MSIL assemblies, and we go and we say, we check to make sure that they're type safe. We check these other qualities about the contracts and things, and then we run it through the Bartok engine to generate the code for the particular processor type. Like an x86. This version of the operating system is running on, and then go ahead and put the pieces into place. The configuration requirements, by the way, is one of the really I hadn't meant to talk about this today, but we'll throw it in. Was one of the things we talk about. So, for example, you come over here and talk about the disk driver. The disk driver has some configuration requirements it needs. It needs it needs an actual disk controller, and the disk controller has to be of a certain PCI chipset number, and there has to be I/O resources. Mm-hmm. And in a traditional system, you kind of plug against the wall, and you hope that the disk driver doesn't use anything more than what it's supposed to do. In Singularity, we actually label in the code, here's all the requirements for this disk driver. And then when we install it, we can actually check and see, okay, I'm going to install a new disk driver. Does it conflict with any other device driver in the system? And we can actually go out and check. And once they say, oh, well, okay, that's kind of nice. But another way to think about it is it's really, really important. Configuration is really, really important because you think about, like, security properties, for example. I can have the most secure piece of code in the universe, but if I install it with a blank administrator password, well, the security goes out the wall, if it's misconfigured. And Singularity gives us a mechanism that we can actually talk about the configuration and actually with software go examine the configuration and see if the configuration required for the code to work correctly is the configuration of the system. And that's a pretty powerful concept.
Absolutely. Really nice.
Sure.
Gets back to composability, doesn't it?
Yep, it's definitely composability.
Yeah. Very cool. So, what do you work on?
Well, that's a good segue.
Very good.
Yeah.
I'll tell you.
Magnus, we're talking about drivers, which relates to hardware.
Yes. So I'll actually be talking about some work that we did recently. That I think can be properly thought of as evaluation work. So what Galen described partially just now when he went over the system architecture, and this has been in the previous Singularity Channel 9 videos as well, is our technique for having processes. Our processes on Singularity look very different from processes on the traditional system. In particular, our processes have a whole bunch of properties that you can't rely on in a traditional system that we get by construction, right? We require that when you write a program that runs on Singularity, you must write it in a safe language, and we verify that it's type safe. And the code that we end up generating and running on the machine is also memory safe, which is largely a byproduct of the fact that it's type safe, plus the interfaces that it has to the system. So I'm not sure how explicitly this was mentioned. I think it was mentioned explicitly in earlier Singularity videos. The way we built the system originally, before some of the work that we did recently, we never would even activate and use the chip's virtual memory features, which operating systems almost always do. And we would run all of the code in the system, process code, this process code that runs outside the kernel, drivers, and the kernel, all of it at ring 0, right, which is the most elevated permission level on the chip. And we'd run it all in the same address space. And we could get away with that and still say with a straight face that each of these processes is strongly isolated and really, truly a process in the sense that people mean it in operating systems. That is, a separate, isolated chunk of code that can be started and stopped by the operating system and won't interfere with other processes and won't corrupt the system state. All of those statements are still true about the processes that we have in Singularity, but they come to be true in a different way. They come to be true because how these processes are built, largely because they were written in safe languages. We only carefully give them access to interfaces to the kernel. We insist that when they communicate with each other that they do so by message passing over channels instead of sharing memory. And when you put all these properties together, you get software isolated processes, right, which is a major new contribution. So some of the work that I've been doing recently is sort of an evaluation of this. Whenever we describe this to the systems community, people's reaction is always, well, gee, that's great. It's so completely different from how we're used to arranging processes on a system, which is to use hardware to enforce the boundary around processes. Right? On a traditional system, you run every process in its own address space, and that's what gives you the guarantee that the process can't scribble on other processes' memory, right? But you have the cost of switching between address spaces, and also to make sure that each of the processes can't scribble on the kernel's memory. You run the process at a lower privilege level, right? On an x86 chip, you run it at ring 3, right? And you run the kernel code at an elevated privilege level, and you mark all of the kernel's memory pages as only being accessible if you're running at a high privilege level, right? That way, if some random process code tries to go and scribble on kernel memory, the chip, the hardware, actually catches the violation and alerts the operating system. The operating system shuts down the process. Right? So when we go out into the community and describe what we've done, people's reaction is always, "Wow, that's different from how traditional systems are built. Is it better? Is it faster? Can we rely on it as much? It's software. It's not hardware. What's the deal?" Right? So some of the work I did recently is, sort of curiously, I went to Singularity and put some of these more traditional features or uses for traditional hardware mechanisms into the operating system when they weren't there before. So Singularity didn't used to have any code that knew how to construct virtual address spaces, and we didn't used to ever run any code at lower privileged. We'd run everything at higher privilege. So I went into the system and wrote a virtual memory engine and the associated logic for creating address spaces and switching between them and mapping memory and all that good stuff. And also, there were a variety of adjustments that we had to make to deal with the fact that now we could, if we wanted, run processes at lower privilege instead of always at high privilege. And that took a while. But what it let us do is a head-to-head comparison of our technique and how things are usually done. And we wound up with a system where this ability to use the traditional hardware features can be used in different ways than they're normally used on a traditional system. Let me explain what I mean by that. On a traditional system, you know extremely little about the code that runs in each process. The processes are typically written in an unsafe language, maybe C, sort of the ultimate example of this, where you know essentially nothing about the properties of the code. So you have to be extremely defensive, right? If you're the operating system, you have to construct this big, heavy hardware boundary around the process, because you can't be sure that the process won't do something untoward. So when I added the use for hardware barriers in Singularity, I created this somewhat different thing, which is more flexible than the mechanism that's in a normal operating system. We called it a protection domain. So here's the picture that Galen drew, and these are largely sort of system components and drivers, although they really are normal processes. And I'll draw some more boxes that are sort of applications. So here are just some applications about which the system knows very little. And Galen, I wonder if you have a different colored pen.
He does always best.
Pick a color, any color.
How about green?
All right.
So a traditional operating system, when it ran each of these processes, it would run each of them in its own address space, right? And at lower privilege. Okay. When I added support for the hardware features to Singularity, I did it in this different way. We have these things called protection domains, and a protection domain is a container for processes. And a protection domain comes with its own address space. But as I say, it can contain more than one process. So in Singularity, with these new features, you can arrange the hardware protection boundaries in this way, right? You can have app 1 and app 2 running in their own address space, but app 4 let's see, this is supposed to be 3. App 3 and app 4 run together in some other address space.
Okay.
And this might initially seem to be, why would you want to arrange it this way? But remember that the nature of applications in Singularity is that we know a great deal more about whether these two processes are likely to interfere with each other than you do on a normal system. In particular, we have very strong reasons to believe that they won't. So because we have a second mechanism for ensuring the isolation between processes, you don't have to deploy hardware in the same places as you do on a traditional system. The question arises, why would you use hardware protection at all if you have this cool software isolation technique that we believe provides just as strong isolation as a traditional system? The answer to that is, well, quite frankly, the isolation techniques that we've built to date still, and this is an open issue of research, rely on the correctness and proper functioning of a variety of sort of hunks of code that regrettably are written by human beings. Right? So for software isolated processes to truly be isolated from each other on a Singularity machine, you have to believe that a few things are functioning correctly, and they probably are, but perhaps you're the paranoid sort. You believe that maybe they're not, right? The compiler that you use to translate the instructions to machine executable instructions has to do the right thing, right? Like if it accidentally mistranslates a section of your code with instructions that'll sort of scribble on arbitrary memory, you're in trouble, right? Because hardware isn't backing you up. The runtime components that supports each of these processes has a trusted piece that's in charge of a variety of things, implementing certain system-sensitive operations like channel communications, communicating with the kernel, things like that. Some bits of that code is unsafe. It has to do sort of raw pointer manipulation, stuff like that. So it's possible, in principle, that could contain bugs, as I say, written by human beings, right? And it's still an open research problem how to write a completely verifiably safe and correct garbage collector, or even to write a garbage collector in a type-safe way.
Yeah.
Right?
How do you do that?
Hey,
How did you do that, Galen?
the answer is we don't know yet. So our garbage collector is written in C#, but in the unsafe version.
Because you're using pointers.
Yeah, because we're using
You have
pointers.
to, right?
Yeah, and we.
But we also have a researcher working on...
We have people working on this problem
Mhm.
of how do you write a verifiable garbage collector and how do you verify the code that comes out of the back end of the compiler.
But now let me ask you this. With the garbage collector that exists today on the CLR, one would argue is a pretty damn good garbage collector written in unmanaged code. So are you saying, what if you had a garbage collector like that is, I mean, it's not trustworthy because it's not safe and it doesn't go along with the contract of your system, but heck, works nicely.
Right. Well, so it's like Windows or any other. There's two ways you can decide whether to trust a piece of code. One of them is you ran it under enough circumstances that you'll trust it for as far as you've been able to see it. The other one is you actually can verify it, prove some properties of it, and say, "Yep, I'll just trust it under any conditions because I know that I verified that it will work under any conditions."
And researchers prefer the second approach.
And the advance of the state of the art is if we can get to the latter
Sure.
case, right?
Absolutely.
And
You can write a garbage collector in a verifiable language,
Yeah.
right? Type safe.
So certainly we know how to write a garbage collector and apply regular engineering principles to it, to test it, run it through a variety of stress scenarios, and this is what they've done on the CLR, and this is what, we were talking about engineers and, what's the difference between, what an engineer does for a living and what a researcher does for a living. It's what engineers excel at, right? And Microsoft in particular has gotten very good at having a process for, turning the screws on software and shaking out the bugs and making sure that it's of good quality. More so than people give us credit for.
Absolutely agreed.
So
It's still black art.
it is still a black art, but that's definitely a valid approach, right? You say,
Absolutely.
well, look, I'm an expert in engineering. I've applied a huge number of man hours to testing this thing and verifying it, and I've got this crack test team. I'm here to tell you that it behaves the way you want it to. That's
Okay.
a perfectly valid approach. But the second, even stronger approach is to say that even without having tested it in all possible scenarios, I know by construction, because I examined it and reasoned about what it does, that it will not misbehave in at least the following specific ways.
Absolutely. And that comes back to composability again.
Well, let me say a few words because we've actually done a lot of work on this, and this is a really important point: is that doing program verification of any sort, using tools or using any kind of formal techniques, is hard, and you're not going to do it for everything. I mean, we're not going to take Windows. We're not even going to take all of Singularity and be able to verify lots of properties about it. We'll be able to do things like type safety and Singularity. But there are certain parts of your system that are just so important. In our case, it's the underlying runtime system. It's the garbage collector. It's the runtime system that sort of goes in every single process. It's basically the part of the system that we really, really depend on sort of at the lowest level, that if the SIPs don't work, then the whole artifact that we built on top of it isn't going to really work either. And so there are certain parts of your system where you're really willing to spend a lot of resources to do the verification, as well as testing. I mean, we've done testing. We've taken all of the CLR type stress tests and applied them to our garbage collector. But, we would like more assurance than that because our system really depends on that. And, it's an interesting thing because, the hardware guys also do it this way too. I mean, there's no guarantee that the hardware virtual memory is correct. right? I mean, our experience seems to be that it's correct. We've used it for a long time. People seem to have a fairly high degree of confidence. And the hardware people who implement it also apply a lot of these formal techniques to assure that the designs are correct as well. But there's no real guarantee there either. And so, what we're working towards is getting to this higher level of confidence. And, it may be a combination of we've been able to run Singularity for a long time and it works really well for lots of people, plus we've been able to verify small parts of it that are really critical for us. And so that's really what we're aiming for. And what Mark said is absolutely right, is that people are a little bit uncomfortable with the software techniques because software seems to have a lower degree of reliability than hardware does in terms of sort of having bugs in it. And one of the goals of Singularity is to sort of push that and to try to see how far we can get away from that problem with software. And part of it is the verification that we mentioned. Part of it is throwing a lot of resources at really trying to prove the properties of the system that are crucial.
So some of the work that we've done recently along these lines is to try to emphasize that it's not always an either or, right? It's not that you have to abandon all the ways in which you're used to building software and the mechanisms that you're used to relying on. When we went out into the systems community and described the work that we did, the common reaction that we got was, but it's all software, so I have to trust a lot of the software, right? I have to trust your compiler, I have to trust your garbage collector. And we said, that's true. But the work that we did here to add traditional features back into Singularity emphasizes that when you know about these new techniques, you can use them selectively where they're appropriate, right? So this mechanism that I just described, where you can group together applications and choose to draw the hardware protection boundary around them in groups, chunks, rather than having to do it around each of them individually, lets you tailor the cost of the hardware protection, which acts as sort of a backstop to our software techniques, so that you can make the trade-off on the system as you see fit.
Right.
So that,
and I should point out that in a lot of cases what we're talking about here is security. And one of the things that we've learned about security is that the only way to really get it is to have defense in depth. You can't just have a single mechanism that if the attacker gets past, they've got everything. And so, one way to look at the hardware domains that Mark's talking about is that it's really the defense mechanism if the software fails. And what Mark's work showed is that you can use this in an incredibly flexible way. You can put it where it's appropriate. So you can draw these hardware boundaries around code that you don't trust, and you can draw it really fine around code that you don't trust. And you can put large groups of the things together. So for instance, you might put all the system processes in the kernel in one of these domains because we wrote it all and we're sure it's correct. And we trust each other enough that we're willing to run in the same address space. But this application that came along from some other group, we may not trust it at all, or we don't know what it does, and we sort of say, okay, let's just have this additional level of defense in case those guys are really clever to figure out some hole in our system, and we'll have hardware protection as well. And similarly, if you were doing this commercially, you can imagine lots of different architectures that make sense. If you had sort of applications that communicated a lot, you want them in the same hardware address space, because communication within an address space, Mark hasn't really got to this yet, is much cheaper. And so that's one pressure pushing you to put things that communicate together in the same address space. Conversely, if two processes don't communicate at all, there's not a real cost on the system in terms of putting them in separate address spaces. And so maybe you do that just to keep them isolated. Things that you don't trust, maybe you put in a hardware protection space to get some more isolation from the rest of the system. Maybe if you're running multiple copies of the same application, you run them all in the same address space, because even if you don't trust it, what is it going to do? It's just going to affect other instances of the same application. It's not going to affect the system. It's not going to affect some other application that's running in your system. So you have a lot of flexibility here. You can trade off sort of protection against cost in lots of different ways. And it's basically perfectly malleable, because we allow you to sort of put whatever SIPs you want in the hardware domain that you choose.
So I would mention two things here. One is that we have two gross controls now in the system. You can group the processes, as Jim described. You can also control whether a group of processes is protected from the kernel. These are sort of two independent controls, right?
So the kernel is protected from the group of processes, is the way you want to say it.
Yes,
right?
Yes. I guess the kernel isn't like
The operating system.
We trust the kernel. It's these other people we don't trust.
It's true. It's not that the kernel is going to reach into your program and disrupt you. It's that we fear that the program is going to reach into the kernel. So with this flexibility, as Jim says, right, if you're the system deployer and maybe you wrote some code or you have high confidence in some drivers, you can situate them in the same protection domain with the kernel runs at the same high protection level, which is
the way Singularity was built originally, right?
Uh-huh.
Communication with the kernel is extremely cheap. There's no context switching overhead.
Because it's a microkernel, and that's one reason.
Well,
right?
But with
No.
all this, remember that the software techniques for ensuring a very high degree, really, of isolation of those components that you've nonetheless chosen to group in the same hardware domain.
Gotcha.
Let's go back to that. I mean, microkernels don't all have this property. Right, the context switching comes about because you're switching between address spaces and perhaps switching the processor permission, this processor ring you're running at the protection level of the processor. And other systems, other microkernel operating systems, going back to the early ones, used hardware protection. The kernel lived in its own address space. It ran at ring 0. They had lots of pieces of the kernel pulled out into their own processes, but those were running in separate hardware address spaces. Typically they weren't running at ring 0, and so the context switch between one of these processes, which might be a driver, say, and the kernel was reasonably expensive. There was a lot of work into making it cheaper, but they never really got it to be as cheap as like procedure call in the kernel.
And this is why in some circles microkernels came to be sort of a dirty word. Right? People would make fun of them because they're like,
yeah, I'm saying here. So I'm going to come to the board really quick. So Mark's used this dotted line to represent a hardware protection domain. Okay, and with a traditional microkernel,
There's one
you
around
literally have a hardware. So the stereotypical, what is a microkernel? If you went and asked, computer scientist professor, your professor, he would say a microkernel has a hardware protection domain around every single device driver, every subsystem, every single process. Okay, and this is why, and they're expensive because every time it doesn't matter whose system. Anytime you cross a hardware protection domain, it's more expensive than just a software protection boundary. Okay.
Sure.
And the fun thing about the Singularity implementation that Mark's done with our protection domains is we can actually make Singularity look exactly like one of these traditional microkernels. We can put a protection domain around every single process
and then measure it.
And see what the performance looks like. The other thing we can do is, we can take all the protection domains out. Okay, the way you should think about the way we normally run Singularity is we just have one protection domain that includes everything running on the system, one hardware protection domain. Okay, there's an alternative implementation, and we have this great tech report that Mark,
Which is publicly available.
That's publicly available that discusses these various. So one of the variations is, what would Windows look like? Okay, where would I draw these? Well, the Windows looks like I'm going to draw a blue line. Windows looks like this. The kernel and all the device drivers and the subsystems all run in ring 0 together. Okay, and then my IIS and its plugins run in separate processes. Okay, and we can actually create that implementation.
But again, I'm missing something because Windows isn't quite as good.
Yes, right.
Because there's no boundary here between the kernel and the device driver, and so if the device driver dies, the kernel dies.
So we can.
So they are moving a lot of stuff out of kernel mode.
And in which case they will pay the hardware performance penalties, right? So what we can actually do is create this implementation that has. Remember, we've got belts and suspenders. Well, we put our suspender around the outside because suspenders are not very fashionable and they're expensive, and then we just use belts between the software isolated processes between these processes, between the within the kernel, for example.
So can we clarify one thing though for the people in the audience, including myself, who aren't computer scientists or hardcore research developer engineers? Let me ask you this, because this is interesting stuff. With a name like Singularity, it's got to be good. So why do I need this? I mean, my question to you is this: can I have two software isolated processes, two SIPs sharing the same address space?
Yes.
But if I didn't use this hardware protection layer that he had, that immediately seems to be a flaw in the architecture.
Let me try to recap. I think.
But let's talk about that.
Why is it a flaw? I mean, I'm not sure I understand what your point was.
Well, I mean, they're sharing the same address space, so they could.
They aren't really sharing the same address space. You can think of them as coexisting in the same address space.
Okay.
Because they're SIPs, they live in entirely disjoint sets of pages in the address space.
This is the key.
There's absolutely no sharing between those two SIPs. There's not a single address on any part in either of those SIPs that's shared with the other one, because they have their own set of pages, and those pages are allocated out of the same address space.
And furthermore, we have
Got it.
reason to believe that the processes can't come to improperly concoct an address in the other processes.
That's right.
range.
That's the
type
language safety. It's basically, it says you cannot take one of your pointers and mutate
Merge
it
it.
so that it points into the other guy's page. And similarly, you can't take an integer and turn it into a pointer and make it point into the other guy's page.
And this is
And this is really important.
Yes,
this is
this-
why the SIPs work.
This is very
Okay.
important, and this sort of gets back to something that I said at the beginning about revisiting assumptions, right? Traditional systems, often you don't think to go back and revisit your assumptions, right? Traditional systems are built around the idea that you can't rely on any properties of the code that you're going to run in the process, right? There could be anything in there. You have no idea, right? It might-
Traditional systems were designed back when people were writing code in assembly language.
Right.
And there was no way to verify that you were going to use the pointers correctly.
And we didn't have the techniques, we
you
didn't
know,
have the languages.
the follow-on systems were written in C, which doesn't have much more of a type system than assembly language does. And so again, there's no way to verify these higher level properties.
But we have a
And
way now.
We have a way now, and it's called, higher level languages with language safety. And, programmers are pretty comfortable with it now, thanks to all, 30 years of evolution, culminating in Java and C#. And, they believe that they're better languages for a lot of reasons. And what we're saying is, not only are they better for the reasons that you guys are familiar with in terms of being better for programming and fewer errors and easier to find the errors, but we can also architect the system totally differently.
To take
we
advantage of it.
We can take advantage of it, and we can do things like that make the system faster. Everybody thinks a higher level language, Java, garbage collection, C#, garbage collection, slow. And what we're saying is that doesn't have to be true, is that if you actually sort of say, okay, well, we have language safety, maybe we don't need this hardware safety. Can we throw that out? Yeah, we can throw that out, and we can make the whole system run faster, even though it's written in a high-level language than it could before. I mean, we have benchmarks where we're literally an order of magnitude faster than conventional operating systems for sort of fine-grained operations. And the reason for that is that we are getting rid of all the hardware protection, which has a lot of overhead, which was necessary for the unsafe languages, the assembly code, the C code, and saying, okay, if you're running a safe language, you're paying maybe a little bit of a penalty for language safety. And we've actually measured that. It was another experiment we did. And we actually we turned off, for instance, all of the runtime checks in our operating system. Basically, the null pointer checks, the array bounds checks. And the system ran 4.5% faster. So it's a pretty minimal overhead. But the point is that we can get rid of the hardware overheads, and Mark hasn't mentioned it, but the hardware overheads can be very significant.
Well, I've got some numbers.
Yeah.
This is something that I actually now regret not having mentioned earlier. We say, oh, well, you can draw the hardware protection boundary in different places. Why would you want to do that? Well, because using hardware actually, as it turns out, is really expensive. And this is another assumption that people don't revisit, right? Traditional systems, you can't assume anything about the process. You have to use hardware to protect it, because that's the only way you can catch the misbehaviors that the process might exhibit, right? You don't know anything about it. But so people, they just sort of throw up their hands. They're like, well, I don't know. Maybe it is really expensive, but I have to use it. People don't realize that using the hardware protection mechanisms is expensive. So here's some examples. So Jim mentioned that we ran the experiment to measure the overhead of the software safety, and it's about 5%, and that's true. Conversely, we did some macro benchmarks where we took one of the experiments that we did, and all this is in our technical report, which is freely available, by the way.
We'll put that in the link in the post.
Yep.
Yeah.
Okay.
One of the experiments we did is we ran a macro benchmark that simulates the load that gets put on a server to run this,
On the file server for web.
on the file system to do the spec web benchmark, which is this standard load benchmark, fairly straightforward for static content on a web server. So we timed it running in the traditional Singularity configuration where all the hardware protection is turned off. Okay, if you just activate the processor's virtual memory features, right? And we still run everything at the highest privilege level and in the same address space, but just turning on those hardware features makes the benchmark run 6% slower. 6.
Okay.
If now you take the application and you put it in its own address space, but you still run it at high privilege, it gets 12% slower than the previous mark, right? And then if you turn on the protection to isolate it from the kernel, which now makes it look like Windows, right? It's in a separate address space with protection from the kernel. It runs 14% slower than the previous mark. So it runs about 33% slower end to end than it did in the normal Singularity configuration.
Okay.
We have a bunch of micro benchmarks too. Like one of our measures is allocating a single page of memory. in the Singularity system beforehand, if you compare that to how much it costs when you've got all the virtual memory engine turned on, or you want a page of memory, you have to find a physical page, you have to find a page in your virtual address space, you have to map it in, activate the mapping, you take a TLB miss to load that mapping from memory to extra memory accesses. It's 5 times more expensive to go get access to a single page of memory if you've got all those protections turned on than it was in the old Singularity configuration without the hardware protections. I mean, there are a bunch of these, right?
Sure, and this is all in the report.
Yeah, it's all in the report. It's 4 times more expensive to call the kernel if you turn on the protections. It can be up to 10 times as expensive to move data between processes, because if they're hardware isolated, you have to copy the data. I mean, this is something that we haven't mentioned, but when everything's running within the same protection domain, to pass data from one process to another, we just pass the pointer. This is another one of the properties. We can guarantee that the process that gives up the data will never access it again. There's a property called linearity. So we can just take the pointer and give it to the receiving process and be sure that that data won't act as shared memory between the 2 processes. So using hardware is potentially very expensive, and traditional systems have to do it because of the assumptions that they're living with. If you go back and revisit the assumptions and build a system around modern techniques, you can get a lot of efficiency.
You know, people shouldn't be too surprised, right? Because all we've done is taken the runtime tests, which, in a safe language, people sort of object to, and they say, oh, it's terrible, you have to do array bounds checks on every array access, or you have to do null pointer checks on every pointer reference. And, those don't go away if you're running in C. They morph themselves into checks that occur in the hardware. They still occur at runtime. They still incur overhead, as Mark's numbers show. They're a different type of check, but somehow you've got to protect that this pointer reference doesn't go and sort of reference a page that belongs to another process. Somebody's got to check for it. And if you can't check it statically in the compiler, which we do in a lot of cases, then what you have to do is you have to check it at runtime. And if you can't check it in the software, you have to check it in the hardware. And this kind of check has a cost. I mean, it makes the processor more complicated, obviously. It makes the processor run slower. And so, things don't go away even though you don't see them all the time.
And we control a lot of moving parts in the Singularity project. One of the moving parts we don't control is the processor. So we have this sort of open question that we're curious about, but that we haven't been able to answer, right? Which is, suppose you had a processor that didn't build in all these features that that you sometimes have to use if you can't make these assumptions. Could the processor run a lot faster? We don't know. Maybe not, but maybe so. At the very least, it would use a lot less silicon.
Well, and in the last, as we're winding down here, I mean, this brings up the question. You mentioned processor. I mean, the future of processing is multi-core. And so are you guys built to really handle that? And I'd like to ask this, as an app developer on your system, what does a multi-threaded application look like?
Oh, you can use
So let's talk about that. So look real quickly.
So,
does it look the same?
Yeah, actually it does.
Oh, by the way, I can show you a demo.
You can?
I'm already, yeah.
All right.
Make sure we have time for the demo.
Yeah.
Okay.
So actually, within a single app, let's just draw the app over here, we have threads. And, the threads are fairly conventional threads, except they're extremely lightweight. We don't allocate a big stack. We dynamically allocate the stack as it runs. So the idea is you can create lots of threads if you need them within there. And we've been experimenting with a variety of ideas. One of them is called transactional memory, which is basically a way of synchronizing between the threads without using locks. So you basically, it's like a database transaction. Each thread runs it, and it has this atomicity property that sort of all the results from the transaction come in, and has an isolation property is that the other threads don't interfere with its execution. And so it gives you a higher level programming model, which we have in Singularity, which we've been experimenting with as well.
Okay, now that does have a processing cost, though, right? An overhead.
It does have some overhead, yes.
Okay.
And we've been
But you're working on it.
We've been working on it. There's a lot of things you can do in the compiler and the runtime system to reduce the overhead. But, again, it's an experimental technique, but there's a lot of interest in this in both the hardware and the software community in terms of building this in.
So, and I guess the reason that I brought that up was that if you have these super powerful processors in the future, right, which isn't very far away,
Yes, today.
then this whole hardware, the stuff that we're talking about, does it really matter? Because I have these super powerful processors that can handle the type of performance things you're seeing on a single core today. If you're able actually to utilize a multi-core properly, which is hard, I know that Dr. Larus is working on that in another project. But the point is, right?
I think these issues are large.
So,
I think these issues are
running out of time.
Yeah, I think these issues are.
I have another tape.
I think the issue of whether you can express computation so that it's parallelizable well to take advantage of the multiple cores is
largely separable from the issue of how you ensure that different concurrent operations don't interfere with each other. On the system.
I think the top level bullet is we've had this contract between software and hardware for decades now.
Mm-hmm.
And everybody has just completely taken it for granted that that's the way things have to be. And we know that it's going to change because of concurrency and multicore. And we can also say that it can change. There's other ways it can change because of Singularity in terms of memory protection, maybe hardware support for different synchronization periods, lots of other things. And it's an exciting time to be in the field because we've suddenly said, hey, this hardware-software contract, it is going to change, and in fact, we can change it in many more ways with Singularity than we can do with traditional operating systems. It's an incredible inflection point in the industry right now.
Fantastic. Well, on that note, I'm going to end this tape. We'll put in another one. We'll watch that demo.
Do the demo.
Okay.
All right.